So, all right. Okay, so I can start, I guess. So welcome to the introduction to finite element method. So so what are we gonna do? Like I would like to first show you the syllabus. I already published the syllabus, so this is going to be a very basic introduction to finite element method, but you're able to learn every detail of the method because I'm teaching like starting from scratch, and you're going to come to a point that you're able to develop your own solvers, even like a very complicated problems, linear, non-linear, like maybe you're familiar with the Navier-Stokes equations, which is the most complicated equation that can even be integrated by using the finite element technique. So what are we going to do? So this is the rough schedule of the class that we're going to start with a little bit introduction and then like preliminaries, of course. So basically, we're going to start with some implementation of one-dimensional governing equations to teach you how we're going to implement actual the weak formulation. Then I'm going to teach you like the techniques of approximation from like the simple first order approximations to quadratic shape functions. Then we're going to do a bit of theory about like the accuracy of finite element method up to mid-exam, which may be like face-to-face. We don't know, like up to March. The education should be like this, I guess. And then we'll see, maybe we continue in the class. So we'll deal with that unsteady problems, weak formulation in 3D. Then we're going to deal with some kind of like diffusion type problems, unsteady heat conduction, and then nonlinear finite element methods. So for the text, I don't use any textbook as you're used to my style. So I suggest a few reference books like the Beth finite element procedures or the one from the publisher Dower, Numerical Solution of Partial Differential Equations by the FEM by Johnson. So these are just reference books, so you don't have to buy. The only thing, like, you should to just follow me on the board, like the lecture notes that I'm going to write down are going to be enough, so you don't need to buy any textbook. So for the grading also, like I'm going to give you like 3 assignments, like 30% of your grade. Like there's going to be 1 mid-exam, like 30%, and a final exam 40%. So you're also able to enroll into the Canvas of this course, which is the link already. I have uploaded this into the class UBS. So that's all actually about the syllabus. If you have any questions, you can ask now. Then I will start actually to the introduction. Any questions? Don't hesitate. So I have like 14 participants for now. Let me see who are, everyone is like listening, I guess.
Yeah.
Yes.
May I speak?
Yes, sure.
How will be assignments like quiz or homework?
Oh, there's no quiz. Like it's not like before, like in the fluid mechanics or the other microfluid mechanics classes, I usually do quizzes. Now this is assignment that I'm going to give you before, like a homework. You'll have 1 or 2 weeks to submit your solutions. And maybe I should just talk about this. This is not a class that you're really going to use any software, okay? So it's not like we're going to use ANSYS or like maybe like Fluent or COMSOL. If you're like maybe heard of like the multi-physics software COMSOL, like all the background, like the whatever happening inside COMSOL is based on finite element method. So you're going to learn actually that basics, and I'm going to give you some like simple assignments, but probably it is like not at the beginning of the semester. It may be even like I can give I will give the first assignment maybe mid of the semester, maybe I'm not sure yet. Like we have to finish first the a real example actually on the implementation of FEM, which is going to happen at the 5th week. So that's like up to fifth week, I guess you're going to have no assignments. You're going to just try to learn the basics. So I'm going to show you like a lot of stuff, even if you don't have, because this is about like, we're not going to use any software. So what are we going to do? We're going to actually write down some simple codes actually to be able to integrate some differential equations. But I'm sure like most of you, even if you're like familiar with the coding, you're not able to apply it to a real problem. So I will show you actually a few examples, like implementation of FEM in one dimension. Probably we're going to write down the code together. The language is not that important for me. You can like, I usually prefer C++ for my research, like, or maybe like you can use Python if you're familiar with, but you don't have to use that kind of languages. You're also like able to do your homeworks actually through the MATLAB. So it's also C-based. It's more user-friendly, that you don't have to deal with the compiler like the black. I mean, like usually like people are afraid of the coding or compiling the coding, or even like the connecting to inversion, or like some linear algebra libraries is a bit difficult, even like to the CPP. So instead of like dealing with that kind of stuff, what I do in this class, I teach you the basics, like the theory and how to apply it to a coding. So you simply show it to the MATLAB, because it's nothing different. So even all of my students, like my master students, they do some trials first with MATLAB, maybe like to see some introductory results, and then they just transfer everything to C++, because the MATLAB is not fast enough if you happen to exceed some limits of size in terms of like the mesh, or like because we're going to loop through some like you're going to use some loops to fill the resulting systems to be able to invert the the resulting linear system, and that is going to require you to use like loops that if it is a bit kind of like, if the size gets bigger, the MATLAB starts slowing down, and it's not feasible in terms of if you consider the unsteady problems. For steady cases, it's like not a big deal. You can always use with MATLAB. But usually, like I work for like our problems are unsteady, so the time is important in terms of even like the inversion of one system. That's why we use the other language. It's not I don't use the MATLAB. I use the MATLAB only for post-processing, but I'm able to show you how we're going to develop a solver from scratch. Even like I will start today, I guess, with a very simple coding example, that we're going to write a simple function that we're going to use it later in the class. All right. Any question? So for the sessions, I guess, like we're going to have like 3 sessions this week, maybe next week, maybe Friday afternoon. I'm not sure yet, but usually it's going to be like at this time up to March. If they decide it's going to be continue like as face-to-face, then we're going to continue in the class after March. But till the 1st of March, we have to like maybe the we have 6 lectures, I guess, to until that date. So we have to be continuing like this. Like I'm going to use the background, like the board on that you're going to see in a minute. I will write everything there. If I need to show you like a coding example, I'm going to just take it down and then show you implementations through the MATLAB if you like. Okay. Any question? Yes, I have graduate students here. Yes. So they're kind of like watching me here face to face, but the undergraduate students are away. I didn't like actually this kind of teaching. But anyway, we're going to handle, I guess. So if you don't have a question, what I'm going to do, I'm going to start probably with the intro. So if you don't have a question. If just one of you can say, we don't have a question, and I will continue. Okay, no questions? Do you have any question? No, I guess. Okay. So this is the first section. Like, it's kind of like Zoom allows us like 40 minutes. So it's going to stop at like after 40 minutes, I will record the session, and then I will continue with the next session, like at the time that I have already shared with you. So this is like, I have spent almost 14 minutes, so I should have like 25 more minutes, I guess, to finish this session. Okay. Any question? Okay, no. So okay, so this I'm recording the screen, so I need to actually write down for you to, maybe like some of you are not able to watch this session live. So I'm going to start writing everything starting from the introduction. And then I will make a really quick introduction to simple coding that we're going to use, okay? And then you may practice later at home if you like after today's sessions. So this is the, let me just go here. So this is the introduction to finite element method. And it's going to be the lecture 1. So I'm going to start with the introduction. So why, I mean, just the name of the lecture is actually finite element, but why do we use it? So the idea is actually comes from the approximation of some equations, like in science or engineering. We define some model problems governing the motion of particles, either in solid or fluid, doesn't matter. And the governing equations are actually complex, like in terms of actually if you think of like the constitutive theories, like the modeling the materials, like if we consider like solid mechanics, there's going to be different stress tensor defining different materials, and the relation, I mean, the resulting equation, like usually it is like the linear momentum balance equation, which is going to be known for the like fluid, like Newtonian fluid has Navier-Stokes equations of motion, or like if I just change the stress tensor, it is going to be any governing equation for example, elastic solid, doesn't matter. But in every equation, like in every problem, we have a model equation. Usually it is going to be a partial differential equation. So the partial differential equations are not simple to solve analytically. Usually it is due to either unsteadiness or nonlinear terms. So what we need numerical techniques actually. So I'm not able to solve every equation analytically. It's not feasible, or it's not possible even. Like for example, if we talk about the Navier-Stokes equation of motion, it is fully nonlinear, and there is no explicit solutions for every problem. Like maybe for very simplification, like simplified problems, there are, but if we like consider the most general cases, of course we don't have, but we're able to solve or find approximate solutions to the equations. So this lecture is actually about finding approximate solutions to the governing model equations of problem from any measure. Doesn't matter. It can be civil engineering, it can be like mechanical engineering, chemical engineering, doesn't matter. It can be from just the like biology, doesn't matter. As long as we are able to model the physics correctly, that means like, okay, this is the governing equation, I know for the problem, then the FEM can be used to find the approximate solution. But if your methods, I mean, if your equations, governing equations, like any partial differential equation modeling the problem, misses any physics from the problem, then finite element method is not going to be help. Okay, it's not going to help because you're not modeling the actual physics. So finite element method is not actually dealing with the model problem or equations. So we're going to be like given the governing equations, and then we will try to find approximate solution to the governing equation. So maybe you may wonder, like, if you need to know physics, a lot of physics, to be able to handle this class. No, you don't have to. I'm going to give you the governing equations. You don't have to be like, you don't have to even understand what is the problem like behind this governing equation or model problem. You don't have to, like, you're not responsible. This class is a numerical, one of the numerical techniques that we are applying to several problems, and I use it for my research, like just one of the numerical techniques. But we use it a lot because we're not able to do experiments all the time. We're not able to do theory every time. I mean, like the theoretical works are difficult, or even like to understand or go to some theoretical explanation, you need numerical results, because this is like kind of like cheap in terms of like the experimental studies, and sometimes you're not able to do experiments. Maybe I'm trying to measure some variables below microns levels. I'm not able to do it with the experiment, but I'm able to actually find approximate solutions if I have the correct numerical solution. And the finite element methods is going to provide us this. Okay, so let me just write a few stuff here. So we have a model equation. Just like a PDE, that is like partial differential equation, to be approximated by finite element methods. Okay, so why do we need the approximation? I'm just writing down the summary. So we need the numerical methods for what? Generally, as there is no analytical solution, as there is no analytic. Maybe I'm just doing some spelling stuff, but just ignore analytical solutions, or we are not able to perform experiments because it is expensive to perform every experiment. That's why this kind of studies are called numerical experiments. As long as like you validate your solver with some theoretical problems, then you can just vary the parameters and do numerical experiments. Okay, so so the model equation comes from, of course, the physics. Okay, so as long as you include the all the physics, so FEM is able to integrate the governing equations for example, we can tackle like the hyperbolic or parabolic, or maybe elliptic type equation. So you can just search for the like what is the physical mechanism behind like this kind of, like maybe you heard of this kind of equations in the differential equation class, like what is hyperbolic equation, what is parabolic equation, what is elliptic equation. You can just go back or Google the like the physical uses of this equation. For example, if you consider the heat conduction, like diffusion type of problems are like parabolic, okay? Or hyperbolic is like kind of like convective problems, like the shock, like any problem, like kind of earlier equation of motion. It has like the convective acceleration. If you consider like the Navier-Stokes equations of motion, we have like the mass acceleration is equal to resulting forces on the fluid particles. Like this is body forces plus the surface forces, which is kind of like diffusion type on the right-hand side, but the left-hand side is kind of like convective type. So these are kind of like defining the types of differential equations, but it's like just I have written these three types to give an example of the like the capability of the finite element technique actually to be able to approximate the solutions. So the technique is actually started with the it actually started with the kind of like in terms of civil engineering like problems. I mean, the people who work on the this kind of like problems have developed the method, but later they have learned that okay, this technique is actually very useful even for problems including like the which actually stem from like the several scientific areas like biology or like the engineering kind of problems, like maybe like the mechanical engineering problems like diffusion type or like modeling the models governing the motion of fluid particles, blah blah. Like it's kind of like very popular now, and the reason behind the popularity is actually it has some advantages compared to other numerical techniques. So let me just write down a few other numerical techniques, other numerical techniques. Are, for example, finite difference. Maybe you are familiar with the finite difference from the numerical methods class for your from your undergraduate education, which is the most common technique in which like the any differential is replaced by a quotient rule. For example, suppose I have df over dx is going to be approximated by, for example, f at I plus 1 minus f at I divided by some delta x. What is this? For example, we just suppose like this is like the solution domain x. We just evaluate the f at I and at I plus 1, and then we have the distance between the two finite difference nodes, delta x. So I'm kind of like, maybe this is the f function f. I'm like looking at any point, the derivative of f may be approximated by a quotient rule. Like this is the first order Euler equation. So the governing equations actually are their differential equations, and usually they are continuous or discontinuous, doesn't matter, but we are able to define f, for example, at any point in space, so infinitely many points. And we're not able to actually solve or find the solutions at any point in space. That's why we use numerical techniques to be able to handle actually the kind of like I'm trying to find a solution at the desired point, and this requires like a discretization of the problem. Like kind of this differential equation, like not differential equation, actually, this is the first order just the df over dx. I just approximated by using like 2 points in space. Kind of I am discretizing my governing equation. Like this is how we do it in finite difference methods. Okay, so there is also like finite volume. This is another technique. This, for example, finite volume is actually like if Fluent actually using this like maybe I should come back. Finite difference is not, I mean, it's used, but not that popular in terms of engineering problems, not able to handle everything in terms of actual complex geometries. It's difficult to find actual discretize the domain, I mean, in terms of mesh, but finite volume is one of them, like finite elements. There are like boundary integral for example, another technique. We can just extend this method, a lot of stuff. And finite element is another one. But the FEM is actually has some advantage, like over this methods like mentioned here, to tackle complex geometries as well as the discontinuities. Okay, maybe I'm just doing some spelling mistakes. So, okay, so this is just for you to rewatch later. So any question? I have spent almost 30 minutes, so 10 more minutes to go before the end of first session. Do you have any questions? Do not hesitate to ask. So the interesting thing with FEM is this one. For example, in with FEM, we are actually kind of like converting the equation. Like there's a PDE. For example, we're going to have something like, for example, temperature diffusion with time with some k partial square t partial x square. So we have like 10 more minutes, okay, to go. Anyway, so this is like one of the parabolic examples of a partial differential equation. It is called PD because the temperature depends on both time and space, more than one variable. Like if we work with, for example, finite difference, we would replace like the derivative terms with the finite difference approximations. But in FEM, we actually restructure the equation, restructure the PDE to weaken the differentiability requirements. Okay, what do I mean by this? In a minute. Like, for example, in this example, like I just have written like this is like the coefficient for diffusion of the temperature, but this doesn't have to be uniform. What if I have a space, I mean, the coefficient varying as a function of space? What is this? For example, I may have this kind of material, like a part of this may be different kind, like maybe I have one part with different property, another one this like this one, and maybe I don't know, just putting some random shapes to, you know, like this is going to be like my domain. I'm looking for like maybe like I just put a temperature boundary condition here. I don't know, whatever it is, like maybe this is going to be T1, and I'm looking for what is the diffusion of this temperature through this body. But you see, like there's going to be here and here discontinuity in K. Okay, K is a function of space X and Y. So that this equation for this two-dimensional problem should be written as like the divergence of K of X, Y times the gradient of temperature, okay? And what we see, so this is in two dimension, okay? Like in one dimension, this turns out to be an equation like partial T partial X, not X actually, this is time, is equal to partial X, this time K of X, partial T partial X. So what does that mean? There is going to be like the K here, conduct like this coefficient is a function of space. And if you just consider like one of the, like take a section here, let me just change the pen. Maybe like I'm considering just this part, okay? If I just consider this section, it's going to be like a one-dimensional bar. Like this is X is equal to 0, this is X is equal to L. I'm going to have maybe like this part is one part, another one is equal to maybe this one, okay? So this is going to be like the different region, okay? So I'm going to just, this is one material maybe, another material, maybe this part, okay? And maybe another one here, like it's like maybe the combination of three kind of materials. It's just maybe like like plastic or whatever, and I'm looking for what is the conduction of heat from left to right. And what I see here, like at this point, there's going to be a jump in K, because like this requires the derivation of K with respect to space X. So there's discontinuity, and there are ways to tackle this problem, but in finite element, we're kind of like weaken the this differentiability requirement, and we're able to deal with this kind of situations very simply, because we're going to restructure the PDE in a weak form. Okay, so this is going to actually help us a lot. And in terms of also like the dealing with the complex structures, like I may have any weird domain, and I'm able to actually discretize this domain, like kind of like, because we're going to find the solutions in this space, like we are going to call this omega. I mean, this is the space omega, and the boundary is going to be the partial omega, and then we're going to just discretize this domain, like by using triangulation, for example, which is usually like termed as meshing the domain. So I'm going to mesh this domain with like maybe triangles, okay? Like, and then this is going to actually generate us the a discrete problem. Okay, so like I'm going to fill this whatever it is, and then at every point, like here, maybe I should use another color. I have going to put some, like at every node, I'm going to define the unknown, for example, temperature here. Okay, and I'm going to find the solution at these points. Okay, and by integrating this equation. Okay, any question? Okay, any question from the office? Huh? No? Okay. So this is just the beginning, like idea kind of introduction to the finite element methods. So it doesn't matter what is the governing equation. For every individual problem, there is a way of dealing with, like either you can change the approximation space, like this, there's this continuous Galerkin, continuous Galerkin, like usually we're going to deal with the continuous Galerkin in this class. But I have some, like I have full Navier-Stokes solver using the techniques I'm going to teach in this class. So developing a Navier-Stokes solver is not a simple thing, I guess, in terms of complex problems. At least like single phase is simple, multi phase is difficult. But we're able to tackle this kind of problems for, I mean, considering the actual implementation of the finite element techniques. Like we're going to learn everything, like from linear problems to nonlinear problems, steady to unsteady, from simple mesh generation to like everything, like from scratch. We're not going to use any library. And I'm going to start today, I guess, by teaching you how you find the approximate solutions, integrations. Like we're going to, because I said here, we're going to restructure the PDE in a weak form. This is going to end up with an integral, and this is going to require us to find solutions to integrals, like computation of, for example, like f of x, integral over the domain omega. So how am I going to deal with that? I mean, it's not simple to find the results of the integrals analytically as a function of space. So I'm going to start teaching you today, like giving a simple integration, starting from the examples, and then I will continue with the what is the schedule? Like this is intro and preliminaries, I guess. Maybe I'll continue with the approximation methods later. Usually, actually, I'm going to teach you today the Gaussian quadrature. I actually take this to the first week because I want you to be familiar with the coding a little bit. So I'm going to like mix a bit the syllabus, like the schedule here. Maybe I'm going to, doesn't matter, we're going to go anyway in like I usually I'll have time to finish the topics, so it doesn't matter. So this is going, I usually like give example for the Gaussian quadrature later in the class, but I have decided to give it in the first week because you need to deal with the coding a little bit. So I'm going to show you today a simple written writing for integration of some simple functions, kind of like the library you're used to maybe use like in MATLAB or Mathematica. So we're going to write down today, I guess, in the following lectures. So I have almost like 1 minute left. So if you don't have questions, ask. If you don't, I'm going to stop, give a break, and start in 15 minutes, I guess, to the next session. Any question? Nope. No one is asking anything, I guess. Okay. So I'll see you, I guess, at 14:25, I guess. I don't remember even the, I don't know. Let me just check here. I have, yes, 14:25 in the scheduled meetings. So if you have any question, ask by email. So see you in 15 minutes.